Hi there, so this is a video just going to take you through question 4 from paper step 2 2014. Why have I chosen this one? Well, the honest reason is I was just going through my old step folder solutions and I noticed that in the 2014 step 2s I'd only done question 1 to 3. So I was like, oh my god, I'm going to have to do this. I probably did those questions as well at least 10 years ago, so maybe I got stuck when I got up to here, maybe I just started to enjoy my holiday and do other things, I don't know. But yeah, anyway, this one looks quite fun. I worked through it, and I'd say straight away, this isn't necessarily great prep for the MAT, just because this is quite clearly, you know, A2 maths, as in like we're using integration by substitution. That said though, it's great practice if you're doing step and you've already done the maths A level in your first year. If you're a further mathematician and you do the maths A level in year 12 and then you do the further maths A level in year 13, then this is a good question for you to do. Particularly if you're looking at doing step in the future, it's a great question for you to do. And whilst I said, oh, it's not necessarily great practice for math, it kind of is actually, because the difficult bits of it are the algebra, they're not necessarily the technique. So as long as you've met integration by substitution before, this will be a good question for you to do. If you haven't, okay, then you'll probably have to leave it for a little while. Remember as well, if you want me to do any questions in particular, just leave me a message in the comments and I'll happily go through particular questions if I can get my head around them myself. Yeah, you'll find the more practice you do on these, the better you get. Okay, so let's stop waffling and let's get on with it. It's a good question as well, actually, this, for certain like little things which aren't in the syllabus necessarily for A level, which are really, really useful for these extension papers. I'm thinking about arctan x plus arctan 1 over x equals pi over 2, which you definitely need in part 2. Anyway, but we'll talk about that in a second. Let's do part 1. Okay, so I've got to show, using a substitution, that this integral equals 0. Yeah, that's kind of weird, you know, but I go, you know, start off straight away by thinking, okay, well, let's just write down, you know, good problem solvers just start by just writing down the question and getting a feel for what's in it. So it looks pretty horrible. X on x over a squared plus x squared, a squared x squared plus 1 dx, that's supposed to be equal to 0. Well, let's let u equal 1 over x and just go with what they're asking us. So du is going to be minus 1 over x squared dx, and so that means as x squared, well, minus x squared du equals dx, and x squared will be 1 over u squared, we're going to have minus 1 over u squared du equals dx, yeah? And so what have we got here? We've got, you know, just kind of go about it thinking, okay, let's just see what happens. So I'm going to be swapping the dx with a minus 1 over u squared du. I'm going to put the minus outside. I need to change the limits as well. Now, remember these are the limits for x, and so if you were to do 1 over b, well, that would be 1 over b up here for your u, and likewise 1 over b is just b, so it's going to be b down here. Yeah, I'm just reminding myself that I've changed the limit there. Okay, so x becomes 1 over u, ln 1 over u, over, okay, we're going to have a squared plus 1 over u squared, multiplied by a squared x squared, well, that's a squared over u squared, isn't it, if you just think about it, plus 1. Try and make sure your a's look different to your u's here, otherwise we're going to get in trouble. Multiplied by, well, dx is being swapped with, I've already accounted for the minus, I just threw it outside straight away, 1 over u squared du. Okay, cool. Well, this is one trick you definitely want to be aware of before you do math or step, yeah? That minus flicks round the limits, yeah? Generally speaking, and this is like, you know, I normally tell this to my A-level students as well, because I think it's a really important trick. The minus of a over b f of x dx is absolutely the same as b a f of x dx. Now you might think, well, why is that? Well, if we assume that when you differentiate g of x, you get f of x, that would mean that f of x would integrate back to g of x, yeah? So if I'm just going to do a very quick proof of this statement, that is equal to that. I hope you've seen this before though, because it's a really well-known result. So here's my little proof. Let's assume that the derivative of g of x is f of x, and therefore f of x will integrate back to g of x. Then this will be g of x minus between a and b, which is obviously the minus of g of a minus g of b. Yes, I plugged in a a and b there, but that's the same as g of b minus g of a, isn't it? And g of b minus g of a is obviously going to be what you'd end up with if you just integrated from b to a f of x dx. I hope you can see what I'm getting at there, and that's just because f of x is going to integrate the g of x again, so you're just going to do g of b minus g of a. You can see it's just basically saying you would have subtracted the limits the other way around if you had a minus outside here. That's exactly what would happen. So I'm going to use that result first, and I use that throughout this question, so that becomes b 1 over b. And now what am I going to have here? Well, the ln of one of u I'm going to make minus ln u, and then I'm going to make that minus ln u, and I'm going to put that u on the bottom here, and I'm going to times this u squared into this first one, so I get a squared u squared plus 1. Notice I don't times both brackets by u squared, do I? Because if I'm doing 5 times 3 times 2, I don't do that as 15 times by 10, do I? No, that's nonsense. 5 times 3 times 2 equals 30, yeah? And therefore it's the same as 15 times 2, yeah? Or it's the same as, if you like, 3 times by 10, yeah? You don't times both of those products by 5. I've seen loads of students ask me that, really clever students as well, and it's like, no, you're getting confused. So I'm just multiplying that u squared into that first bracket in there, and this u down here is a consequence of the 1 over u. I've just put that u down there, and then this is a squared over u squared plus 1 du. Okay, right, I still want to, what am I thinking now? I'm trying to think about what I'm trying to show. I'm trying to show this equals 0. My feeling is, right, if I've got a minus, yeah, what I could do is I could turn this into, if I had a u squared down here and I times it into this one, I'd have exactly the same as what I'd started with, but all x is replaced with u's, except there'd be a minus outside. Now, that made me think, great, that is really, really, really good. Let me show you why. It's easier to see once it's written down. So what I'm going to do is I'm going to times top and bottom by u. That's going to become a u squared. I'm going to times it in this one here. So I've got a squared u squared plus 1 multiplied by a squared plus u squared du. Yeah. Now this is identical, but instead of x's I'm using u's. Yeah. Now notice though it's the negative of what I started with. So what have I shown? I've shown, let's give this a name here, let's call this I. Yeah. What I've shown is that I equals minus I, because the letter is unimportant, yeah? Like, this could be, I don't know, P's instead of U's there with a DP on the end, or Q's instead of U's there with a DQ on the end. It's exactly the same integral. It equals some number, you've just changed the variable. In essence, you've basically made the substitution let u equal x, which would be the craziest substitution ever, and then you end up with the identical, the identical value of the integral. So what have we shown? We've shown that I equals minus I, yeah? That's what I've shown. Hence I equals minus I, but that means that 2I equals 0, or in other words, I equals 0, and the result is established. Yeah? If you can ever show, let me put it another way, like, because I think this looks really like, we're overcomplicating something simple here. We've shown that an integral with limits, which therefore takes a numerical value, and that numerical value may well be in terms of b or whatever, is equal to the negative of that numerical value. Now, when do you ever get a numerical value equal to its negative? There's only one situation, and that's if your numerical value is 0. 0 equals minus 0, if you like, but 4 doesn't equal minus 4, and 6 doesn't equal minus 6. And that's why you've proved that the integral must equal 0. So there we go, that was part 1. Let's try part 2. Part 2 is different, it really is. It's not the same trick or anything. Sometimes in the easy integration questions you're sort of like being taught a trick. I wouldn't say that's the case here. I'd say each part of this, and it's worth remembering in this in STEP and math, just because some questions, part 2 depends on part 1 and part 3 depends on part 2, or they link up, that's not always the case. And obviously anyway, with show that questions, you wouldn't need to know how part 1 is done to necessarily get part 2 right. So don't assume that questions are always going to be like linking to each other, and if you can't do part 1 you definitely won't be able to do part 2. That is not the case. Yeah. Okay, so I'm going to do the next part. We're going to try and find the value of arctan x over x, and they've told us same substitution. They're showing how cool this substitution is. It is a cool substitution, definitely. Okay, so let u equal 1 over x again. and then du is minus 1 over x squared dx, and then for exactly the same reason as last time, minus 1 over u squared du is equal to dx. And so let's make our substitution. Okay, don't forget these are the limits for x. When you plug them in, you're going to get 1 over b here and b again. Yeah. Arctan x is going to become arctan of 1 over u. Then we're going to be dividing by 1 over u, which, yes, I know is the same as timesing by u. Okay, dx needs to be swapped with minus 1 over u squared du. Yeah. And now I'm going to do that trick with a minus and swapping the limits round again. And I get arctan of 1 over u. Okay, if I times that u squared by 1 over u, I get 1 over u. And therefore, I've got, yeah, that's just that's going to be u squared over u. So it's just going to give me u du. Yeah. Now, what have I ended up with? I've shown, what have we established? We've established that it's exactly the same as what you started with if you swap u's for x's, because it doesn't matter, except this is 1 over u, yeah? Now this is the first bit, when I worked through this question the other day, this was a bit where I paused and had to think. I flew through part 1, I was happy with the way that went. Part 2, I got to this point, I was like, interesting. I thought that must be relevant, yeah? We've shown, we can just work over here now. We've shown that, okay, the integral between 1 over b and b of arctan x over x, we've shown that's got exactly the same value as b and 1 over b as arctan 1 over x. Let's use x this time instead of u, over x dx. Cool. So we know that that's the same as that. Now, one thing you want to know for your mat and your step is that there's formulas for arctan a plus arctan b. Yeah, it's very, very similar to compound angle formula. It's kind of like the opposite result to the compound angle formula you get. I need to do a video actually of all the kind of trig tricks which you might need to know before you do that, because there's lots of them. Those weird formulas they give you in a formula book which are never tested at A level, they sometimes are tested in further maths actually, involve what I call them factor formulae. They're worth knowing. There's tons of trig stuff which you're just not taught in normal A level, which can pop up in the extension papers. I'd love to do a video on it. Anyway, this is one of those moments, because what I can say is that therefore that if I call this I, once again, I suppose I should use a different letter to last time, but I'm not going to, because I like to give my integrals names in the integral. It's really, really helpful. Therefore 2i is just going to be the result of adding these two together. Now they've got exactly the same limits. And these kind of tricks you get used to. Plus arctan of 1 over x over x. Obviously we've got a common denominator here, yeah? Now why is this so nice? Well, let me just do an intermission. I believe that arctan of x plus arctan of 1 over x is pi over 2, yeah? It's this kind of stuff, knowing this kind of stuff gives you massive, massive advantage in these extension papers. You've got to know stuff like this. Now, why does that true? Here's my little proof, yeah? It's a very short proof. I'm just going to do it in the case when theta's between 0 and 90, yeah? Okay, let's call this x and this 1, because then we've got tan theta equals x, and therefore theta is arctan of x, yeah? Cool. Okay, what's this angle up here? Well, that would be 90 degrees, or pi over 2, minus theta, yeah? And so what I can say is tan of theta minus pi over 2 equals 1 over x. And the reason why I'm doing it this way round is so I can get arctan of 1 over x, yeah? And so therefore I can say, clearly, arctan of x plus arctan of 1 over x is going to be equal to theta plus, oh hang on, I've done that, why have I written that down as theta minus pi over 2? I meant pi over 2 minus theta, I'm sorry people. You see how many mistakes I make, there's loads. Okay, plus pi over 2 minus theta, and that equals pi over 2, yeah? Now what are we really showing here? Well, you know, when you do arctan, you're finding an angle, yeah? And if you do arctan of the reciprocal of the two sides, then you're finding the other angle in the triangle. And those two angles always add up to 90 degrees. It's very similar to the result that arc sine x plus arc cos x equals pi over 2. I don't know if you've ever seen that result before. It's a very similar thing. It's just because if this is theta and this is pi over 2 minus theta, well, you know, this is h, this is like, let's call it a q, just to be different. Yeah, can you see that sine theta, well, let's say, yeah, should we do it on the other side? Let me just label it on the other side, put a q here. Can you see that sine theta is q over h, but cos of pi over 2 minus theta would be equal to q over h as well, and therefore we can say that theta is arc sine of q over h, and I'm going on a little tour, complete what do you call it, I'm going off piste here, I'm going completely off topic. Pi over 2 minus theta is going to be equal to arc cos of q over h. So if we call our q over h x now, you can see that arc sine x plus arc cos x equals pi over 2. Yeah, very similar to that result. You want to be good with those kind of results. They pop up in the extension papers, they really do. Very rarely though do they pop up in normal A level. Okay, so why is this cool? Well, it's cool because I can immediately turn that into arc tan x plus arc tan 1 over x. Well, that's pi over 2, and I'm just going to pop that pi over 2 out here, and then I've just got 1 over x dx. That's easy to integrate. Let's put the 2 with the pi over 2 and make it pi over 4. Let's integrate that, so we've got ln x between b and 1 over b. Now everything's going to work out lovely, because we get ln b minus ln 1 over b, but that's the same as ln b plus ln b, so that's 2 ln b from log laws, and so that's pi over 2 ln b, as required, I think. Oops, sorry. Yeah, pi over 2 ln b. Okay, last part. Okay, using the result that from 0 to infinity 1 over a squared plus x squared. Let me actually move this question over so I can see it. Let's give ourselves some more space. So part 1 and part 2 I was pretty happy with. Part 3, yeah, I didn't mind it actually. I had a good guess on what k would be here. We need to choose a suitable value of k and end up by, you know, and integrate the bottom function, yeah, which is 1 over a squared plus x squared, which is an arctan before you square it. Anyway, that's the typical arctan integral. It's in the formula book, but we want to work out the square of that result from 0 to infinity, yeah, because apparently it's pi over 4a cubed. Okay, right, let's try and prove it. Let's let u equal, now the first thing I tried was just 1 over x, yeah, because that's what I tried before, and I thought it might be wrong, but you know, I just went with it at first. Actually, I didn't try 1 over x, I tried a over x, because I thought, well, I'm probably going to times in the brackets, yeah, so I didn't get it right first time, because a is not the 1, it's actually a squared. First, I just want to show you though why I got the hint that it might be a squared. When I was rearranging this, I just thought, well, I'm going to have x squared over a, yeah, minus du equals dx, yeah, and I was a little bit unhappy that that a wasn't squared, because I thought, well, I'm probably going to then times that into the brackets here and hopefully have some nice things happen. It just didn't feel right to try it with a, and so I just went with a squared at this point and thought, well, great, it's a constant, so I can just put a squared there, and a squared here. And then I realised, particularly in the rearrangement, it was here where I really decided, no, it almost certainly is a squared, because you're going to get u squared is a to the 4 over x squared. That means that you could have u squared over a squared is a squared over x squared, and that started looking really nice and symmetric. I like the look of that, it just looked right. And also here I thought, well, this is great, because if a squared over x squared is u squared over a squared, then x squared over a squared is going to be a squared over u squared. And I've got a good swap there for my integration by substitution. Okay, so that's what I started to do. Okay, so first thing to notice is, if these limits are in terms of x, yeah, well, when x is going to infinity, you're going to be doing a number divided by infinity, a constant divided by infinity, which is basically 0. And then when x is 0, loosely speaking, something divided by 0 is infinity, or if you prefer, and this is much more the way mathematicians would put it, as the bottom tends to 0, the value of that division will tend to infinity. You know, think about a divided by 0.1 is 10a, a divided by 0.01 is 100a, and let's use a squared divided by 0.001 is 1000a, yeah, and so on and so forth. So, you know, clearly as the bottom tends to 0, the top tends to infinity, and therefore the limits are just going to swap round, which I kind of like, yeah. Okay, so what else have we got here? I'll put the minus outside because I figured I'm just going to swap the limits round again, because it's probably going to be a similar kind of thing to that happening. Okay, what have we got here? We've got 1 over a squared plus, now x squared, if you remember, x squared is actually going to be equal to a to the 4. I don't know if I've written down x squared anywhere here. If you think of these two swapping round, a to the 4 over u squared multiplied by, okay, dx, well that's the same as minus, I've already accounted for the minus, I've thrown it outside, a squared over u squared du. Cool. Okay, let's swap those limits round, get rid of the minus, let's leave the a squared on top. And then I thought, well, look at this, I've got an a squared there and an a squared there, so I could take the squared out, the a squared out, and then square it to give me an a to the power of 4. Now this is where you want to be super confident with your algebra. And I'm going to try and put that u squared in. Now, what slightly disappointed me was when we're putting this u squared into that bracket, we're going to have to think of this as kind of like a, let's not use a and b because I'm already using that. If you think about how you do, you know, if you've got p squared times q squared, you can of course think about that as pq all squared, yeah? No surprise there. So I'm going to try and force this u into those brackets by basically ignoring the squared on it. Oh, I'll cancel that into 1 over a squared, and I'll put that outside, I'll park it there. So I've got 1 over, now I'm trying to put the u into here, that's going to give me a u plus, now that's going to be an a squared over u all squared du, yeah? And I looked at that and I thought that don't look too nice really, but I thought, well, let's just roll with it. I wasn't sure here how I was going to get to the end. I had to, like, you know, do a little bit of self-belief here. Okay, and then I thought, well, let's make this u squared over u, so you've got u squared plus a squared over u all squared du, and the reciprocal flips it, so you end up with 1 over a squared, infinity and 0, u squared over u squared plus a squared squared. Now the reason why I like that was it looked similar, not the same, but similar to what I started with, and I thought that's a big hint. Like with the other two, when you end up with something similar to what you started with, have a good look at it. Now the other thing to say is, have you noticed in every part of this question, the way I've got it right in the end is by actually giving my integral a name. Ian the integral. It's really, really useful, yeah? So let's call this I, yeah? Now this is an old trick which I've seen before, and it comes in really handy. Look at this, and imagine instead that you had 1 over a squared multiplied by, right, let's make this u squared plus a squared, because then that's one of the squares will cancel there. And then we're going to have to compensate by putting a minus a squared on, with u squared plus a squared squared, yeah, du. Now why is that really nice? Well, because I can now just look at u squared plus a squared over u squared plus a squared squared and make that just a u squared 1 over u squared plus a squared, which they've already told me the answer to, because they've already told me what that integrates to in the question. I'll show you in a sec. So this is going to be 1 over u squared plus a squared du minus, and then I'm going to have an a squared over u squared plus a squared, which is pretty much identical, squared, which is pretty much identical to I, isn't it? Yeah. Let's have a look at this. They've already told me. Let me just show you. They've already told me that this integrates to pi over 2a, and whether it's, you know, x's there and dx's or u's and du's obviously makes no difference. So this is going to be pi over 2a. Lovely. Yeah. Now what about this? Well, think about the a squared moving outside. Then you've got I. You've got exactly what you started with. So you've got a squared I here. Yeah. Let me show you. Yeah. Look at the integral we started with. We started with this integral. I is that integral. Yeah. Now the fact that we've got u's instead of x's makes no difference at all. And so that's just going to be a squared times by I. Yeah. And this used to come up all the time in the old syllabus where you had a reduction formulae in the further maths. I think it's in Further Pure 2 if anybody's studying Further Pure 2. But yeah, it's really handy giving your integral a name. It really is. Now when you do that times that, the a squareds are going to cancel. So you could say that 2i equals pi over that times that, 2a cubed, and hence I equals pi over 4a cubed. And there you go. So that is classic step 2. Step 2 is difficult, yeah. There is a strong argument to be made that step 2 is harder than step 3. Try the questions, and once you're really confident with further maths material, and step 3 isn't always on further maths, but it's supposed to be aimed at that kind of side of things. But yeah, you know, you'll often find that step 2 is the worst. It really is. So I hope that video was useful to you. I hope it made sense. There's always an integration question in both step papers normally. So yeah, make sure you can integrate. They are good questions to do. They're some of my favourites. So yeah, good luck, keep up the hard work, and I hope that was useful. Bye bye.